let me introduce you to myself. I am a bright cluster of photons from another world that is in the 12th dimension. And this is the best fiber ever, named Ayça Yıldırım, in this reality. But we would like that if you call us Andromeda. And our purpose today is sharing what we have learned about optical quantum computing by reviewing the somewhat latest studies of your species. Also, I approach this speech as a whole creation of its own, so I have color-coded the slides. This red slide is the root of my research. It is related to soil and earth element, and it gives the ground for me to research about this topic and stick the landing, hopefully. So I started my research by asking these questions: why and when quantum computing term has come up? Right, we need to start from the beginning. And what makes it so special? What are the requirements to realize physical quantum computing? And finally, what kind of role photonics can play for this project? My presentation has these main parts, and the first two parts answers the first three questions, and the third and fourth part answers the last question. So, orange is about creativity and related to water element. And here we see that we have new kinds of problems that require a new creation, a new quantum computing. So around 1980s, it was seen that physical computers are capable of simulating quantum mechanical systems. Like they cannot map the wave function of an electron in a molecule because they don't have enough bits. And even if you discretize the observables of the system, the probabilistic nature and uncertainty principle makes it impossible for digital computing to simulate quantum mechanical systems. So naturally, if we have a computing system that is based on that works with quantum mechanical principles, this would solve the problem. So why is it so special? If we have a quantum computing, we can, for example, map our brain, map our consciousness, or we can model cancer cells. So even if there's a cure for cancer already, which is marijuana, cannabis plant, so we can find drugs, new drugs. We can model traffic, like optimize traffic lights and stuff. But not every task is sped up equally with quantum computing. So it is not for the foreseeable future, it's not going to replace classical computers, but for certain tasks, it gives exponential speed up, like this factorization of Schwartz algorithm. Okay, this yellow page is about power. It is related to fire element, and it gives the fire to keep on researching. For example, this field's objectives are realizing these systems, so it keeps the research going. Anyways, okay, what do we need to actualize quantum computing? We need a scalable, well-characterized qubits. Well-characterized means we completely know its possible state, and we know how it interacts with its environment. We should be able to initialize these qubits, because imagine repeating the same measurement for probabilistic schemes of quantum computing. We are doing the same measurement, we need to set the same photon states, so we should be able to initialize it properly, measure it properly, and they should be controllably interacted with each other to realize universal set of logic gates. We will see this has some problems for due to nonlinearities. It should be well isolated from the environment so that the coherence time will be longer than the logic operations. And these last two requirements come from quantum network. For quantum communication, we should be able to transmit bits between specified locations. Then we have flying qubits, and we should be able to convert between flying and stationary qubits in quantum memories. So this green slide is the heart of the topic. It is related to air element, and with air there comes some understanding. Okay. So we have two approaches. One is based on discrete variables, the other one is based on continuous variables. So qubits, prior to measurement, their state is a linear combination of the basis states ket0 and ket1. Alpha and beta are probabilistic amplitudes, meaning that alpha square would give the probability of qubits being measured in ket0 state, as similarly for beta magnitude of alpha square. So here the information is coded in alpha and beta coefficients, but we can choose several ways of encoding. I mean, we can have several basis states. One common practice is having polarized full polarization encoded qubits. Here, ket1 state is vertical polarization and ket0 horizontal polarization. We see a metal-based counterpart here. Another way of encoding information is path-based encoding. Here, through a polarizing beam splitter and half-wave waveplate, you can convert between polarization encoding and path encoding. Like polarization beam splitter sends the, vertical one here, and that's the horizontal polarization path, and this gives pi phase shift, so they're both horizontal at the end, and they are encoded in paths. This is a Bloch sphere. Bloch sphere represents all possible states of a qubit by using two real numbers. Normally, to represent two complex coefficients, we would need four real numbers. But Bloch sphere uses the phase difference between the states, between basis states, and the angle coming from the relationship between these probabilistic amplitudes being one. So we only need these two angles, and now we can present all states. Now, I think qubits are more popular than qmodes just because they are easier to describe and understand. So for qmodes, we are going to be a bit careful. So this is an arbitrary state of qmode, stick at the top, written with the wave function. Now the information is being encoded in the wave function. So in this approach, photon is considered as a quantized electromagnetic field. And qmodes are system of arbitrary number of electromagnetic fields of different frequencies, different modes. Now we can have infinite amount of basis states, and this is where actually the power of quantum computing lies in the photonic wave approach. We expressed it in terms of infinite basis states. So imagine you have just a bunch of photons out of these electromagnetic fields, and you have their superposition. And we can express this in phase space by using position and momentum quadratures. This is like having this superposition of electromagnetic fields and Fourier transform it. But Fourier transform with some uncertainties. Now we set position and momentum quadratures. Even if they are named so, these are not about position or momentum. These are about the amplitude and phase of the electromagnetic field. but they still hold the same uncertainty principle. So in Fourier space, we can't have single points because of the uncertainty. Therefore, we have quasi-probabilistic distributions, which are named as Tengner functions. And if we have a Gaussian state of light, we can express this in the linear superposition of Fock states. This is Fock state cat 0, cat 1, and cat 2. So, is it clear?
Yes.
Okay, now we know how to represent them, we know what they are, we know how to represent them. Now we need to perform some operations on them. Single bit gates are, for qubits, simply rotations in Bloch sphere. And all of possible rotations can be accomplished with using half-wave plate or quarter-wave plate. Alright, so okay, there's a half-wave plate arranged in a way that after wave goes out, there's a pi phase shift. This is the transformation matrix of this wave plate. It doesn't matter, we just know that this theta is 0. Then we have only this pi phase shift with this term. My point is, by using these wave plates at certain configurations, at certain angles, we can achieve any linear transformation. Hadamard gate is an important one. Imagine like you are getting state 0, and then in the output you can measure either state 1 or 0 with equal probabilities. So it's like a randomizer, but actually what it does is rotating pi rotation around its z axis. Go back. Pi rotation around this axis. If we put two Hadamard gates next to each other, it would be a complete rotation and they would cancel each other. But on its own, it's a randomizer. And for qumodes, these linear transformations, these operations are linear transformations to this function, like squeezing, displacing it, rotating it. These can be accomplished with these things, but I will leave it there. Okay, now, again, to really tap into the power of quantum computing, we need to have entangled states. Because imagine having, like these are entangled states of 2 qubits. Imagine having 3 qubits, so we have 8 entangled states. And if we apply C0 operation, it's automatically in parallel applied to 4 states. So it increases exponentially. So we need to have these entangled states. But photons have low interaction with each other and with the environment. So for photons to interact in this way, we need a medium. And this requires, for example, C0 operation has control bit and target bit. When the control bit is 1, it flips the target bit. But this requires very high nonlinearity, and currently we don't have such material. So this cannot be achieved with only qubits with discrete approach. Therefore, okay, but for this continuous regular approach, there are some ways to work around it. So this is an example of a nonlinear transformation named cubic phase gate. So this is an example. Of course, these nonlinear transformations are not possible for this either, but there are 2 solutions. One is using a hybrid system, combination of CV and DV approaches. For example, exciting a dual rail system, and every time it gets excited, it emits a single quantized electromagnetic wave, single photon. So this is one way, but I'm going to talk about here linear optical quantum approach, which induces this nonlinearity with respect to number of photons. So it has a probabilistic nature. This is from KLM's scheme, and a probabilistic CNOT gate is realized with this NS gates that I'm going to explain, and with beam splitters. So this is NS gate, and it has an arrangement of beam splitters and phase shifters. And by arranging these at certain angles, certain configurations, we can determine the amount of this shift. And when we set it to -1 by phase shift, we can use it to actualize a CNOT operation. This happens here only for the case we have 2 photons in this input state. So, and to know that this bit field is performed properly, we should measure 1 photon here and no photons here. When this happens, we know that phase shift occurred with phase shift occurred, and this happens with 1/4 probability. So there. Okay, and this CNOT gate works for the case that we have 1 photon in cat 1 and 1 photon in cat 3. Yeah. And then we have the beam splitter. After the beam splitter, we can either have 2 photons here, 0 here, or the opposite. And for both branches, this NS gate operates with 1.4 probability, and it becomes -2, 0, -0, 2. And here, this beam splitter again separates them, so we have 1 here, 1 here. This has success rate of 1/16. Alright, a new color. This is about the element ether, Bakash, but I think it is pretty much the same thing with dark matter, dark energy. It is, and this blue is about expression. So here, finally, after getting some understanding of the topic, we are expressing, and we have an idea, we are expressing pros and cons. Okay, so these trapped ion-based systems require, for example, they love liquid nitrogen. But optical quantum computing works at room temperature and atmospheric pressure, and photons are inherently noise-free and has low interaction with environment. However, this probe smears out as we go to a continuous wave approach, because even if they have low interaction with environment, they can still get absorbed, scattered. Therefore, if you lose 1 photon for continuous variable approach, our state changes a lot. Yeah, we see that we can easily manipulate them with these linear transformations. And it is ideal for quantum communication because we already have existing background like transmitting technologies, virus and stuff. Yeah, this problem, we've seen that okay, we don't have this nonlinear medium, so we are inducing this nonlinearity with measurements, so it becomes probabilistic. And okay, sorry. Here we set this happens with 1/16 success rate, and when we connect them next to each other, the probability rate decreases and decreases, so it's not actually practical to use it in a quantum system. There are certain ways to increase this success rate, and quantum entanglement is and band measurements makes it possible, but that's maybe time for the topic for another presentation. So there's a whole other world behind these things. Okay, yeah. And this indigo color is about intuition, and it is about foresight. So this is just my idea of a possible quantum computing scheme at some point of its evolution, I think we will have like few central matter-based quantum computers, you know, at like cold temperatures and stuff, and they will have again matter-based qubits for the interfacing with the network, quantum network. Quantum network will work with photonic qubits and again for interface. And I think these will be connected to several less strong continuous variable optical quantum computing devices. Okay, so this is purple, this is my expert opinion. Okay, I think to realize a quantum wave computing, we need a quantum leap, but every improvement counts. And I would like to ask, what if we already have a working quantum computing system? So I color-coded these pages, and I treat it as its own creation. So all these different aspects, like root and the heart of it and the brain part of it, actually we have it in our own beings too. Imagine them like your frequency components that are experiencing time at different rates. So there are similarities and patterns everywhere, and every technology we see around is based on what we have in nature or what we have in our bodies. And actually our brains are basically transceivers, and it is actually quantum computing. Like we are maybe like quantum detectors that with our thoughts we are collapsing the possible realities, collapsing the wave functions. This is why we can be the creator of our own realities if we focus where our attention goes. So I believe we already have perfectly functioning quantum computers, but sure, I think after all this research, we are going to figure out that there's actually a quantum network too, which is called Ethernet with our transceivers. So hopefully this bridge will be closed with these research, and then everything will become science at some point. And finally, to the camera, I am on to you, fake gurus. This is how it's done divinely and galactically. Andromeda out.